Cool. Well, I'm happy to introduce Michael Gourlay, our speaker for today. Michael is one of the HoloLens leads, and he's worked on, he's one of the original creators of the spatial mapping project, for example, and he's worked on other aspects of the project. He has interesting backgrounds. He has a degree in philosophy and another one in physics, which is always a good combination. He was working on things like computational fluid dynamics for his PhD, and then somehow got interested in video games and worked at Electronic Arts for many years, which is one of the leading game companies, before he somehow got to Microsoft and HoloLens. And I think today he's going to tell us about some of the technology behind HoloLens, which is very relevant for building applications.
So, as Steve mentioned, today I'm going to tell you about how augmented reality platforms work. Not enough to build one, but enough to know how to use one in a way that exploits its strengths and avoids some of its weaknesses. So I'm going to first tell you a little bit about myself. Some of that Steve just mentioned, but this time it will be with pictures, so that'll be more compelling. Normally, I would like to have people ask questions during the lecture. Because of time constraints, I'm not sure whether there'll be time for that or not, but Steve said that after this, we can adjourn to a neighboring room where we can do a Q&A session. So if there's I don't know if there's a projector there or not, but I mean, what I'll try to do is get through all the content here, and then I can entertain questions over there and go from there. So first I'll mention that, so as Steve said, I used to do computational fluid dynamics as a research scientist, and that involves a lot of visualization and simulation, which has a lot in common with video games. As an aside, I still do that stuff as a hobby, and so I write a series of articles for Intel, and so you can go and look up how to make fluid simulations for video games. So as I mentioned, so simulations and visualization also apply to video games. I was wanting to work on video games, and so at some point I just started doing that. And I ended up working on Madden and a few other sports games. And while I was there, I created this visual effects system that creates all of the particle and visual effects that you see on the screen, including the smoke. And actually the light beams up there are a sort of static particle effect, and the little balloons and all the fireworks and the blood and all that stuff is my system. That system is apparently still in use today, even though I left there. After I left, or actually while I was working at EA Sports, I also taught at University of Central Florida at a program called FIA, which is the Florida Interactive Entertainment Academy, which is a graduate program that teaches people how to design, program, and do art. It's this multidisciplinary program. And I just learned this year that we got rated, or they, not me anymore, but that program got rated as the number one graduate school for game development by Princeton Review. So I'm pretty proud of that. I was one of the founding faculty members, and so I got to toot my own horn. I've been there years ago. So more recently, I've been working at Microsoft, as Steve said, on HoloLens. Originally, I was hired as a game developer. I was asked to prototype how to use surface reconstruction. I didn't like how surface reconstruction worked in the platform, so me and two other game developers rewrote the surface reconstruction prototype and ended up championing that. And so that's actually the thing that shipped in the product, is the thing that you see in there. I happen now to be the lead of the head tracking system. I'm going to, in this talk, describe both how tracking works and how surface reconstruction works, again, to the level that would be generic across all AR platforms, because I'm not supposed to talk about specifically my product. So you have to imagine that what I'm really saying is how a notional AR system might work. And so this would be generic across all of them. Okay, so first I want to describe some AR basics. I think probably a lot of you in this class are familiar with the basics, but I want to frame them in a certain way so that it allows me to kind of talk about it in a more modular way. So let's look at this video. So this is from George Klein. He's one of the pioneers in augmented reality. He wrote a paper called PTAM in 2009 that has sort of been widely cited. And he's one of my colleagues at Microsoft. So what's going on here is that there's this illusion of this, this boy on this field, and this is a very powerful illusion. And most people think of this as being what augmented reality is, and that's certainly an important part of it. So I want to kind of break this down as to what's going on here and why does this work? Why does it seem like Cartman is actually standing there? There are a few ingredients to what makes that illusion work. I guess I'll let it play. One of them is that he seems locked to the world, meaning that, as the camera is moving and the back, the real scene seems to be moving because of the fact the camera's moving. Cartman is moving in exactly the same way that the real world would be moving. So that's what we call, world locking the hologram. Another aspect of it, though, is that Cartman is occluding what's behind him. So that gives him a kind of substance. And there's another aspect that this video doesn't really, I haven't demonstrated, or the fact this video might not actually do any kind of simulation, but the other aspect is that he's not following through the world. So I want to talk about how we achieve all these different aspects. So it's not just rendering holograms on top of other things. It's specifically how that they're rendered. So object appears world locked. It includes the real world, and it seems to obey physics. Right? It's not falling through the ground. So this kind of rendering, I want to contrast with another form of rendering, which you've definitely seen in the movies, and this is called additive rendering. Here, light is being added to the scene. It is not replacing the scene. And this is the kind of rendering that you would see in a see-through display. This is obviously a Hollywood depiction of that, but in HoloLens, if those of you who have worn them, it's hard to take a picture through the thing, right? But if you've worn a HoloLens, and I think most of you have, this is the kind of render technology that's there, and I think Daiquiri has the same thing, where it's literally a projector and it's shining light directly into your eye. The side effect of this is that you cannot render black, because it can only add light, it doesn't subtract from it. So if you want to have a solid-looking hologram, this is my first tip of the day, you have to render using bright colors. If you want to render, an assassin wearing a black cloak, you're kind of out of luck, unless you can come up with some creative way of making that seem like he looks black, but he actually isn't. So you want to pick bright colors, so cartoony characters are going to probably look good. There's another kind of rendering that's composite rendering, where the real world and the virtual world are being rendered in the same way. So you can't do that with a see-through display. You have to do that with a pass-through display. You can imagine maybe someday see-through displays will also have sort of per pixel dimming, in which case they'd be able to essentially render black. I haven't seen a display like that. So so this is composite rendering, where he's doing this augmented reality. He's using all the same tricks that we would use for augmented reality on a see-through display. He's just doing this through a camera, and they're both Iron Man. See. So another aspect of augmented reality and virtual reality is that both have this aspect that they're always first person. So if you're thinking about game design, you have to recognize that no matter what you do, it's always going to be from a first person perspective. And there's no like cut scenes where you can go and take a third person perspective or whatever. It's always going to be from the first person perspective. And that implies not just what you see, but also that the controls will always be in this kind of first person perspective. There's no analogy to an omniscient perspective, neither from the rendering aspect nor from the manipulation aspect. So I just want to show this AR application where somebody can sculpt, in their own 3D space, where they add stuff. By now, so I composed all these slides before a lot of these things were available a few months ago. I don't know if you've noticed, but in the past few months, suddenly there's been this proliferation of VR and AR headsets. So I created this slide deck in January, which is already horribly out of date. Right, this is the world we live in now. This is awesome. So there are much more sophisticated programs like this now, but they all have the same basic idea, which is you're creating things from this first-person perspective. So one of the interesting things about holograms and about headsets that stay, if you're wearing a headset like HoloLens or DAQRI, and you want to do some kind of telepresence, one of the things that's easy for people to forget somehow is that it sees what you see, not the other way around. So, for example, one of the things that it can do very well is the scenario here where there's a girl who's wearing a HoloLens and she's looking at the sink, and she's also got a virtual window that she's placed on her wall and where she sees this person she's talking to. Meanwhile, the guy is talking to her through a tablet. He's not wearing an augmented reality headset, but he can see what she sees. And so he can draw on the tablet where that tablet is representing what she sees. And so what he draws is it's showing up in her world as a hologram. So meaning he can actually create holograms in her world, and that way he can give her instructions about, here's this piece of pipe, rotate it in this direction or whatever. And so they're both sharing not only the real world view, but also the holographic view simultaneously. So I'm calling this shared outward perspective, and by outward I mean from her perspective. So in contrast to that, and I would say that this is a form of telepresence. It's not the kind that we would canonically think of telepresence. That is more like this, so here's this from another movie where people are having this meeting and some guy's hologram shows up in place of him in the same room as a bunch of actual people. And here's Sharon Azadi's research on this that he called holoportation. He released a video on that recently. In both of these cases, in order to capture the person, you need to have other sensors that are outward looking inward. And that's what that's in contrast to, sorry, I said outward looking inward. They're outside looking inward. So in contrast to this, where you're the person who's sharing your reality sees it from your perspective, and here it's this opposite direction, right? You have this outward looking and outside looking inward view of stuff. So the point is that if you want to have this kind of experience, you need additional sensors. You can't just do that with a HoloLens by itself, unless you had a bunch of people in the room all wearing HoloLenses, and then you could throw something like that together. In other words, if you had two HoloLenses, one person wearing one and the other one using it just as basically for its sensor array, you could probably pull something like that off. And from what I hear, you actually have quite a few HoloLenses. So you could imagine creating, sort of a room or an environment where you had like maybe 3 or 4 HoloLenses looking inward. No one's wearing them, but you're just kind of using them for the sensors. It would be a super, super expensive way to do that, but you have a lot of HoloLenses, so you can pull it off. So I just want to do a quick recap of the things that I've mentioned so far. So remember that these see-through displays use additive rendering, meaning you can only add light, you can't subtract it, so you can't render black. You have to design your experiences from a first-person perspective, and that means not just the rendering, but also the control scheme. I didn't mention it, but actually this year at GDC, there were several, not very many, there were a couple of talks about how to design user interfaces for VR and AR. And some of them are crazy. One of them is called the exit burrito, where in order to exit the experience, you have to eat a burrito. Another one that I found really interesting is, so let's say that you have a menu of worlds that you can enter. Each world is represented like a snow globe, and you grab the snow globe and shove it in your, shove your head in it, and suddenly you enter that world. And I thought, that's a really visceral analogy for entering this world, right? You literally stick your head in there and suddenly you're in that world. So if you have, those are interesting. I think that we're going to see this sort of vocabulary of 3D GUIs evolving over the next few years, and it'll be really exciting times. The exit burrito is fantastic. Okay, so then we have these two different forms of telepresence. This one, you would have to have external sensors looking inward, and this is the kind of telepresence that you can have just having a single headset and sharing it with, for example, somebody with a desktop. So before I get into talking about the technology behind these platforms, I want to take a little diversion to describe an aspect of computer-human interaction that I think has evolved now that we've included environments in the scene, into this situation. So, this is sort of the pre-2015 situation where we have humans and computers, and then where they overlap, we have human-computer interaction. This is a field that people have been studying for decades. There are conferences and journals that are all dedicated to this. But now we're going to add a third component, which is the environment, meaning we normally don't think of that as being either the computer or human. It's this third thing. And by just adding a single new element in this Venn diagram, several new regions pop up. In one of the regions, well, we just have conventional reality. We've been thinking about the interaction between humans and environments for as long as there have been humans. So that's not really new. But there's this new region up at the top that I'll call environment understanding, and the overlap between computers and environments. That is the group at Microsoft where I work. We're called the environment understanding team. And I'm going to claim that in the intersection of all three is augmented reality. So I'm going to present yet another view of the same thing. So let's say that we talk about real and virtual on one axis and characters and environments on the other axis. So again, this is the pre-2015 view of things, where you can have real characters, in other words, people, like actual people. And then over on this side, you have virtual, either characters or environments. So again, this is like the sort of computer-human interface, right? So this is all canonical stuff. Now we're going to add one more piece, which is the real environment. And you can see in this graph, we actually doubled the number of edges in here. One of them, again, is not new. This is just conventional reality. But we have two more connections in this graph, which represent the kind of interactions that we can have. So in other words, we can have interactions between virtual characters in the real environment, which is novel. It's never happened before, like not in any kind of mass scale. And likewise, interactions between the real environment and the virtual environment. And so I'm going to talk more about each one of these things. This is probably a very boring looking picture, and that's actually good news, because if this seems like really boring to you, then that means that they've really sold you on this illusion, which is actually extremely sophisticated. What's going on here is that there's a virtual teapot and a real hand holding it, and there's something funny going on. So his thumb is actually occluding this handle, but the handle is also occluding his thumb, right? Depending on which part of the thumb and finger you're talking about. So there's this two-way interaction between the virtual and the real already. This is actually pretty amazing if you think about it, and I'll sort of elaborate on that. But the point is that getting that sort of two-way interaction to happen requires not just that we render holograms, but that we have their 3D structure. So let me sort of amplify this point. So here's a video of a guy, and again, this is composite, not pass-through, but the principle remains the same. So in this situation, when he stands in front of the hologram, he occludes it. When he gets behind it, it occludes him, and then he's going to do this kind of, he'll reach and give him a hug from behind. And you can see both are happening simultaneously. He's occluding the hologram's occluding him. That's actually very difficult to do. You can't do it with just taking a bunch of pictures. Well, you could if you were really sophisticated. But I'll explain more about other ways of pulling that off. So here's another example where instead of just a visual interaction, it's I'll call it pseudo-physical interaction. So here we have a bunch of virtual balls in a real room, and the virtual balls will bounce off of the surfaces in the real room. It's a really low resolution video, I apologize, but up here, this is what's actually going on in the real world. This is what the user is seeing, and on the right column are just representations of the physics, of the sort of virtual physics. So we have some sort of model at the top of the real world, and at the bottom it's just the combination of the models of the real world as seen by the virtual system and also the virtual balls. So so far we have interaction that's visual. So we have occlusion, sort of mutual occlusion between holograms and real things. And also, I've showed in this video, what was happening is virtual objects were colliding with real things, but not the other way around. So I've gotten one two-way interaction, which was visual, and one one-way interaction, which was physical. So now I want to show how to get the other, or an example of going in the other direction with the physical. In other words, a real person controlling virtual objects. So here is a scene where these balls are virtual balls, and the hands are real hands. And this is at this desk that's called a holo desk. Let me restart the video. And as you can see, the person seems to be picking up these virtual balls and playing with them. So here we have real characters interacting with virtual environments in this kind of, in this opposite direction. So this kind of closes the loop, so to speak. We can have two-way occlusion, one-way collision between virtual and real, and then I'll call it manipulation for the other direction. So these are ideas. These are not necessarily things that you can do today on a portable headset, but I wanted to present the ideas. So this kind of wraps up the part about AR basics that I mentioned, meaning you all know, sort of, in some sense, you all know about this already, but I want to sort of divide it up into little pieces so that you can see which of these things can you do today with headsets that you currently have versus what things would require additional technology changes. I have this little spiel about the difference between augmented reality and virtual reality that I'm going to skip because I'm not sure that there's time and it's a little philosophical and I'm not sure that you'll get much out of it. But I'll just mention that I have a spiel about the difference between augmented reality and they're actually different. The only thing I'll mention about it is the word reality in those two terms is actually not the same word. It's a category mistake, meaning that it's not just that one is augmented and the other is virtual. It's actually that the fact that the word reality in both of those terms means a different thing. So here I am just kind of skipping through that. So we can maybe do that in Q&A if people are really into philosophy. Okay, so now I'm going to talk about tracking, and then after that I'm going to talk about surface reconstruction. So, and what I will do is give you just a very high-level view of how tracking can work on a notional system. And again, with the idea that you would know what problems to avoid and what strengths to exploit. So first I will mention this this system called parallel tracking and mapping. I mentioned it earlier. It was the Cartman video used this. This is what George Klein did back in the day along with other people. And so I'll sort of take this piece by piece and describe how the system works. First I want to describe at a really high level what's going on when you do parallel tracking and mapping, and what that even means. So let's say that you have a camera, okay, and it could be a cluster of cameras like that thing, and maybe some of them are looking in other directions, but for the sake of this diagram, when I say camera, you can imagine it could be like a Ricoh Theta that's 360 degrees, or it could be just a cluster of individual cameras. I'm going to call all of that just the camera, or you could say maybe the rig. So each node in this graph is going to be it'll have two meanings. So I'm going to show you a graph in a minute. It'll evolve on the screen. And each node and each edge will have two meanings simultaneously. So this is a node in the graph. And the node represents where the camera is. But it also, therefore, essentially represents a picture that was taken by that camera at some position and time, presumably, but the time aspect doesn't necessarily matter. Okay, so here's this node, represents a camera, and it also, sort of implicitly represents a picture of the world. Since it represents where a camera is and which direction it's facing, it implicitly represents a coordinate frame. I'm going to probably have to go through this concept a few times, because this is actually maybe one of the most important things you can take away from this lecture is this concept. So the point is, it creates a coordinate frame, okay? If you're creating virtual worlds, you're going to have to create those things in a coordinate frame, and so one of the first questions that most game developers or application developers ask about these systems, actually they don't even ask the question, they make the assumption that there is a world coordinate frame. There is not. There is no such thing as a world coordinate frame. That is not a weird philosophical statement, that is a very practical statement. So what I'm going to try to tell you here is how do coordinate systems work in this kind of a system. So as soon as you take a picture, and there was a camera that took that picture, you are implicitly creating a coordinate frame. Like for example, the cameras that are taking a picture of me right now, let's say that their z-axis is going from the camera to me, the x-axis is going from the camera to their right, and the y-axis is going from the camera upward. Or you can, I don't know if I did that right-handed or left-handed, but you get the idea, right? It's creating a coordinate frame. Now let's say that I move that camera and I take another picture. So again, the node represents another location for the camera. It could either be the same camera at a different point in time or a different camera at the same point in time. It doesn't matter. It could even be a different camera. A link here represents two things simultaneously. One of the meanings is that between those two images, there are shared visual features. The other interpretation of that link is that there is a coordinate transform between them. And more specifically, it would be a rotation combined with a translation. Okay, so if I took a picture in with that first camera, and I had this transform between them, and I have a three-dimensional representation of the scene, then that means that even without actually taking the picture, I could imagine or render what the same scene would look like from the perspective of this camera, because I have that transform between the two. Okay. So now I'm going to keep wandering around the room and taking pictures. I take a third picture, and again, a link means that the two pictures have some common visual element, and also that there's a coordinate transform between them. Now that I have a total of 3 pictures, something really interesting happens. If they all 3 share some visual elements, what do I mean by visual element? I'll talk about it in a second, but just the intuitive notion of like, they share something in common in the scene. Like Waldo is in all 3 of the pictures. Where's Waldo? Is that like showing my age, or do people not know what we're Anyway, okay, so in this case, let's say that they all 3 have something in common. So that means that between any pair of camera pictures in this scene, I can create a coordinate transform. Here's the thing though, this will come up quite a bit in practice, is that all of these transforms are just estimates, because in order to figure out what the transform is between them, and you're just using sort of the pictures, there's going to be noise in the camera, or you might have the wrong calibration data, or there could be a variety of reasons why you just haven't perfectly measured where these cameras are. So what you have to imagine is associated with each one of these links, there is a certain amount of error. And so what that means is, so let's imagine that there's no error, and you start at one of these cameras and you walk from here and you go to that camera and you come back to this one and then back to this one. If you combine all 3 of those transforms together, I'm curious to see if people can guess what that transform would be. In other words, if you take a transform from here to here and then concatenate it with this transform from there to there and then from here to here, you concatenate all 3, you should be back where you started. So what kind of transform effectively does nothing to a vector? Identity, yeah, the identity transform. So if you have a cycle in a graph like this, the concatenated transforms associated with that cycle ought to be the identity transform. Guess what? They're not. You won't actually get perfect 1, 1, 1, 1 with zeros everywhere else. That's what you should get, but you won't. When you don't get a perfect, when every cycle doesn't have, doesn't sort of yield the identity matrix, then that graph is called inconsistent. So what that means is which path you take through this graph will give you a different notion of where something is. Okay, so this is basically mapping and tracking. So interesting point. So let's say I keep walking around the room. So let's say I walk in the room and there's a bunch of interesting photos around the room. And so I walk in the room and immediately, I don't look across the room. I'm going to go outside the field of view. So I walk in the door and I don't look over here. I'm just going to look at the wall and sort of circumnavigate the room like this. Right? And I'm going to keep doing that all the way until I get to the door again. That's what this is depicting. So notice, for example, this does not have a common link with this, meaning these 2 pictures don't share anything in common. Okay. So then I get most of the way around the room. Just before I get to the door again, if I want, and let's say I placed a hologram on that light switch right there, and I want to know how to render that light switch, or that hologram that's on that light switch from every point on this path. By the time I get to most of the way around the room, in order to find where that hologram is, I have to concatenate a whole bunch of these transforms together, each one of which has some error in it. And I can construct this graph to be arbitrarily long, right? I can zigzag through this building and not look at the same thing twice. And then I can go all the way back to where I started, and I'll have this really long chain of erroneous transforms. And then at the last second, the last frame will have something in common with the first frame. Just before I get to that point, the error between here and here can be, again, arbitrarily large, because you can construct a path that takes an arbitrary number of hops. And then, so if you looked over at the light switch, didn't take a picture, but we're just rendering a hologram, that hologram could be arbitrarily far from where you put it. The error could be enormous. And then when you close the loop, now if you're standing there and looking there, instead of going all the way around the graph, you have a direct link, and that link presumably has less error. And suddenly the hologram can jump from where it was to a new location. So if you, has anyone here seen that in an augmented reality platform, where you place a hologram, you walk around, and you see it pop around? A few people raise their hands. So this is one possible explanation of what could be happening. So I mentioned before about this notion of common visual elements. What do I mean by that? Well, one example of that is this notion of a feature. And there are probably dozens of papers written about feature detection algorithms. This is just one of them. I actually forget which one I put up here. I think this is fast. I forget. That's sort of my point, actually, is that there are so many different feature detection algorithms that I've already forgotten which one this is. There's this sort of like Olympics of feature algorithms, you know. There are feature detection algorithms and there are feature descriptor algorithms. And the basic idea is that you want them all to be invariant to rotation, scale, and lighting and perspective, right? So one way is to find this kind of local minimum or local maximum in brightness or a saddle point, something like that. If you've ever seen a calibration chart, you'll notice that they tend to be fond of checkerboards. That's because at the intersection of the black squares and the white squares is a saddle point, and numerically it's easy to find that to subpixel precision. So when I talk about that two pictures have something visually in common, I could either mean a discrete feature like this, or it could be, you know, it could be a so-called dense feature or semi-dense feature, meaning it's kind of a swath of, I don't want to say pixels, but essentially a swath of pixels. So this is just one example of a feature detection algorithm. If you want to see, I encourage you to look that up. You can probably, you know, use the search engine and find tons of articles on feature detection. Why does this matter for you who are building applications and not AR platforms or VR platforms? And the answer is, well, if you go into a room where you can't see a lot of features, then you're not going to track very well. So ways of thwarting this would be to have crazy disco lights, although we actually have crazy disco lights in our Holographic Academy that worked remarkably well. Filling a room with smoke, which we had in Holographic Academy, and it actually, I don't know that it worked very well. We didn't have smoke after the first try, but it might have just been because it was obnoxious. Another would be to have a room that just has very few features. So if you have a room that's perhaps really well suited to VR, where it's all black and empty, that might not be so great for AR platforms. They might not be able to track very well. Another thing that's problematic potentially is if you have the same set of features in more than one place, or if you have repeating features. For example, this pattern on the wall here, I bet you anything that each one of these tiles is an exact replica of all the other tiles. And so if you put that, or like a carpet would be a similar thing, like a ballroom where you have the repeating texture. that might confuse certain tracking algorithms. You could imagine, like, if you had, okay, so let's say I stand really close to this thing and I turn on an AR platform, and then I cover up the cameras, and then I come over here, and then let's say that there's no IMU. I'll talk about IMUs in a second, and there's no magnetometer. You have no way of disambiguating. Actually, a better example would be if I looked here and then kind of really slowly walked, and let's say these speakers were gone, and then I uncovered the cameras. If those two patterns looked really similar and I didn't have anything on the sides to look at, it might think that I had actually not moved. I mean, that's a very contrived example and not a very good one. Probably a better example would be if I turn the thing off and then turn it back on again, because that way the IMU doesn't tell you anything. But the point is, repeating textures or having the same poster over and over and over again in all of your rooms would all be recipes for difficulty. So you might want to avoid that. I mentioned IMUs. So the other part of tracking, so there's visual tracking and then there's inertial tracking. Visual tracking is the system I just described at a very high level. And inertial tracking is where you have some way of measuring acceleration and angular velocity and maybe a magnetic field. So that little trio is often called an IMU, or inertial measurement unit. Every cell phone has one of these things. Tracking systems have them, and they're really, really common. You can, they're common and cheap, except for the tactical military ones. And essentially, they do exactly what I mentioned, which is they tell you acceleration and angular velocity. And you can just integrate those to get velocity. You can integrate acceleration to get velocity, and integrate angular velocity to get orientation, and you can integrate velocity to get position. IMUs can generate data at a very high rate, like in the kilohertz range. So if you want to render at a very, very high rate, say 240 frames a second, IMUs can provide really recent data at a very high rate. They tend to have drift, and they tend to have a lot of noise. And that drift and noise tends to be a function of things like temperature, which varies wildly. Not just in the room, but also on a circuit board where these things are microscopic. And depending on whether you're using the CPU more or less heavily, you can actually change the calibration properties of an IMU, and it can give you different readings, right? So the point is that inertial tracking is really great for short terms, short durations. It's not so great for long durations. When you combine inertial, well, I'll get to that in a minute. Actually, okay, this is a great diagram in that I've heard the term used, proof by intimidation. I'm not actually expecting you to understand this diagram. It was just like a nice visual aid to indicate, well, actually it's a terrible diagram. But the point of the concept of sensor fusion is that you get multiple different estimates for the same quantity. In this case, we're talking about the pose of your headset. One of those inputs is visual and the other input is inertial. They each have their problems. For example, the inertial system has these problems of drift and noise, but very, very rapid. The visual system doesn't drift because, well, unless your room is drifting, which, well, can happen if you're in an airplane. If you're in an airplane, your room is drifting. It's just the way it is. If you're in a room that isn't drifting, then your visual estimate is going to be spot on. And the inertial system can be essentially synchronized with the visual system. So the drift problems of the IMU are sort of overcome by the visual tracker, and the slowness aspects of the visual system are overcome by the inertial tracker. Makes sense? So, so I mentioned, like each one of these slides, or from time to time, I'm trying to bring this back to you. So what do you do about it? So an example would be, let's say that you want to have an outdoor experience in, let's say, a forest in a windstorm. So all of your visual trackable features are going to be swaying in the wind. That's not going to do so well with the visual tracker. The inertial system will tell you that you're standing stock still, but the visual system will tell you that you're swaying. So that could be problematic. Another example would be, let's say you're on a bus or in an airplane. There again, you're going to have an apparent conflict between what the inertial system is telling you and what the visual system is telling you. This happens in real life, and people actually don't, do well when their inertial system, like you have a kind of IMU in your head, in your stomach, and your visual system, if those are not in harmony, then depending on how, like some people get sick from that. I'm sure some of you. I'm not even talking about AR, I'm just talking about in real life. Like some people get sick riding airplanes and boats. As an aside, so we had to test HoloLens in preparation to go to the space station. And so one of the things that NASA requires of every piece of material going to the space station is that they put it through a zero gravity simulation, which is colloquially known as the vomit comet. They prefer that you use the term weightless wonder. So anyway, I had to go on this thing and wear a HoloLens and play games. I'm gonna actually save some of that story for later, but please ask me about my vestibular comfort levels. Okay, so all of the VR and AR headsets that I know of, every single one of them has some sort of latency compensation, where basically the idea is that there's going to be a delay between when you start to render a scene and when it actually gets to your eyes. There's a small amount of latency there, and that latency is measured in milliseconds, like tens of milliseconds. Maybe not even tens, it could just be not fractions of tens, so ones of milliseconds. That's enough to really mess you up, like in terms of comfort. So you generally want to do some kind of latency compensation. I'm not going to go into the details of that, other than to say, like, kind of an obvious thing is if you know how much you're accelerating and rotating right now, you can make a prediction very briefly into the future about where you're going to be in about 4 milliseconds, or let's say 10 milliseconds. And so you can render the scene as though you would have been there instead of where you are when you start to render the scene. That's maybe the simplest form of latency compensation. There are more sophisticated forms that I'm definitely not going to talk about today on camera. So that was my little primer on tracking. So remember, the takeaways from that were have an environment that has lots of trackable features. Don't mess with the lighting too much. Don't put smoke in the room. Avoid repeating textures. At least, well, there are mitigations about the repeating textures, but I'll just leave a blanket statement. You'll do better if you don't have repeating textures. I think that was most of it. Oh, right, yes. And the most important thing is about this notion of a coordinate system. Namely, that there is no such thing as the one true coordinate system. So when you have a map of the room, you'll end up having lots and lots of little coordinate systems. And the coordinate system that your virtual object is anchored to might not be, and probably isn't, the same coordinate system that you are currently tracking from. As you traverse that graph, you're going to probably use the coordinate system of whatever node you're closest to at the moment in that graph, whereas whatever virtual object is probably going to be anchored to some other node in the graph, probably one that it's closest to. And as you sort of walk around that room, the path that you traverse in that graph to concatenate all the transforms will vary. And so you can end up having little artifacts like holograms seeming to wiggle or drift or whatever. So one of the things that you can do to mitigate that is map the room very, very thoroughly before you start placing any holograms or before you start your experience. So that, remember that thought experiment I did where you walk around this sort of museum gallery and you look at pictures and don't ever look across the room? That was like the worst case scenario. Never do that. Have people do things like stand on one side of the room and see the opposite. So what you really want is like a fully connected graph so that every node can connect directly with another node, which implies you have line of sight. So that's another good thing to think about, is try to get as much connectivity in that graph as possible, which translates into saying that you want to direct your users to look around a lot. It's really simple. There are other reasons why you want them to look around a lot, and I'm going to speak to that right now. I'm going to switch into talking about surface reconstruction.
So probably have about 3 or 4 minutes.
Okay. The really, really fast version of that is that you can have a special device, which is zooming into the stack tree. Oh wow, that got blurry. So, so you can have a certain kind of camera that is a depth camera. That's not really news. Connect V1, Connect V2, HoloLens, stack tree, all these things have depth cameras on them. What they generate are these things called depth maps, which you can fuse together and get a model. This is my living room, that's my wife. Once you have that model, you can then kind of look at it from novel views, and this is kind of zooming out. This is my apartment in Fremont. So I'm going to skip through most of that and just say basically, once you have that 3D model of the world, which is just a fusion of a bunch of depth maps, you now have something that you can collide against and occlude against. So remember I was talking about these two-way interactions. So tracking is all about placing the holograms. Surface reconstruction is about interacting with them in physical and visible ways. Okay. So the rest of this was going to be a description of how that fusion process works. But I think that probably for the purpose of using it, you don't really need to know how that works, other than to remember that each one of these depth maps is taken from the perspective of a camera, and I've already talked to you about the pitfalls of the coordinate frame of those coordinate frames. So depth maps are really just another kind of picture, and they have the same problems that the other pictures do with respect to things like the coordinate system being kind of squishy. You know that graph I showed you earlier, the pose graph? Think of all the edges as being kind of like they're on springs. And then you have a good idea about how AR platforms view the world, but everything's kind of squishy. It's almost like a sort of general relativity version where like gravitational waves are propagating and messing with this fabric of space. The rest of this is really all about the algorithms used to get all that stuff, which I'm out of time for. I will mention one last thing, which is that these depth cameras, some of these depth cameras have this property that when light bounces, like in a corner, you'll get an overestimate of how far away the surfaces are. That's called multipath interference. The point is that the depth maps have sort of problems, and you should probably avoid expecting really sharp corners and really precise locations for surfaces. I'm out of time, so let's go into the other room, I guess, and take questions. Does that sound good?
All right. Thanks a lot.